Today, we'll be talking a little bit about additive synthesis and not so much focused solely on additive synthesis, but really through the lens of the harmonic oscillator in DZSP, since this is something available to you to use on a DZ seed right out of the box, either in Arduino, DZDuino, which are the examples I'm going to be using today for simplicity's sake, or in C++, with the full libdaisy DZSP combo. So yeah, like before, I've got the simple fix here, and I'm running the patch that you're seeing on the screen right now, which is a very, very simple patch, and I'll demonstrate that now. So essentially what this patch is doing, you're not going to hear anything until I turn some of these knobs, but I have 4 harmonics of the harmonic oscillator. I have it set up for 4 harmonics. The number of harmonics here is defined as 4, and each of these knobs is controlling the amplitude of one of the harmonics. So starting with the fundamental, we have just a sine wave. Then we have an octave up from that. Third harmonic is 3 times the fundamental, so this is not an octave. It's technically like a perfect just intonation fifth, 3/2 ratio, or 1 octave plus 3/2, so times 3, and then finally 2 octaves up. So this is a really, really simple patch. And you might be wondering, okay, how does this work? You could think about it as taking 4 sine wave oscillators and then scaling them, their amplitude, by the reading off the knob, and then adding them all together. That's, of course, one way you could do that. If you do that just sort of naively, you'll end up running, 4 sine wave lookups, which is fairly inefficient, and that doesn't scale really well to a lot of harmonics. But instead, we're using the harmonic oscillator, which is just a single object, and we are setting its amplitudes based on these readings, and I'll walk through how this code works, and then it's just one process call. And this is not doing 4 separate sine wave lookups. We will talk about how that works momentarily, but yeah, that's kind of the demonstration of the patch. And I did also want to show, I've got this hooked up. This is just VCV Rack taking the input from the seed output and then visualizing it on the scope in the analyzer. So there's our fundamental sine wave, and you can see that nice sharp peak on the analyzer. And you'll see, oh, I'm clipping a little bit. I'll turn it down. So I've got evenly spaced harmonics here because I've got this analyzer in linear mode. Normally it's in logarithmic mode, but then you can't see the nice even spacing between the harmonics. So I've got this set in linear mode, and we see 4 harmonics that we can control with the knobs, evenly spaced. So you can also see the wave shape get a little more complex as we bring in these harmonics. And in a little bit, we'll also talk about how that works for, maybe how that looks if you're doing a Fourier or a sinusoidal analysis of a sawtooth or a square wave, what harmonics go into that and how do we replicate that? That's what the other patch does. So I'll pause here before we start diving into the code and the example, and then talk a little bit about how the harmonic oscillator works. Any questions so far? Should be fairly basic stuff, I think, but happy to kind of answer any questions right off the bat from this patch.
Yeah, I think this is actually pretty great. We don't really have any questions at the moment.
Okay, great. Cool. So this is a really, really simple patch in DZDuino. I actually adapted this from one of the stock examples for the harmonic oscillator. It's only 50-ish lines of code. So here at the top, standard stuff you might be used to seeing at the top of Arduino files, patch files, sketch files, whatever they're called. We've got a definition that's our number of harmonics, which is 4, because that's how many knobs I have on my simple fix. And then I've just got a definition for the first ADC pin that I'm using, the first one that's wired to the first knob, and then the other 3 are sequential after that. So it'll be A5, A6, A7. And then I've just got the hardware up here, the seed, which if you've done one of these patches, you should be familiar with that. That's just necessary to initialize all the hardware. and the harmonic oscillator. And this is a template class in C++. So when we actually declare it, we have to use this syntax, these brackets after the name of the class to provide how many harmonics we want it to have, because the actual code, the way the compiler generates templates, that code is dependent on the number we put in here. So we're putting in 4. That's what that constant is. And I'll just open that up really quick. And then we have an array of, again, 4 amplitudes of float type. So these will be 0 to 1, just the amplitudes based on the knobs that we're reading. Helper function here to read, do an analog read, which is 10-bit by default on Arduino, and then return a float 0 to 1. So that just divides by 1024. And our audio callback and our setup. Let's go to the setup first. So just from the example, this is really simple. Just like we do other DAISY-SP objects, we have to init it with a sample rate, and we're using 48 kilohertz here. We're setting the first harmonic index, which is just what harmonic does the oscillator start from. So if I'm setting the frequency here on the next line to 220, which is A3 and A440 12-tet tuning. So this is like A, 1 octave below A4. That just means that the first harmonic is the fundamental. So the first harmonic that we're bringing in when we turn that knob is A3. Then we clear the amplitudes array. So we loop through 0 to 3, so 1 minus the number of harmonics, and then we set all those amplitudes to 0 to start, and then we start our audio callback. In the loop, we are reading each pin over and over. So we're starting from the first ADC, and this is just, rather than do, I could have broken this out into separate calls, but since these are all sequential, we can actually just increment the pin each time. So read from the first pin, increment the pin, store that in the first amplitude, read from the second pin, increment the pin, store that in the second amplitude, so on and so forth. So that lets us read those 4 0 to 1 values from the knobs and assign them to the amplitudes in that array that we have of 4 amplitudes. And then every audio callback, we are setting the amplitudes on the oscillator. And what this call does is it expects this is a pointer to the array. It expects this to be at least as long as the number of harmonics we have. So there's a little bit of unsafe C code, sort of. But you have to just be aware that your amplitudes array, so this is, I just pass amplitudes, that gives me a pointer to the first element in the array. That needs to be at least 4 elements long. It's exactly 4 elements long, so that's fine. And what that does is it takes those values that we read, 0 to 1 for each harmonic, and it sets that on the harmonic oscillator, and then the output will be equal to the 4 harmonics scaled to whatever amplitudes we're passing in there. And that's basically all the code in that first example to get that sort of 4 harmonic synth. If you maybe had 8 knobs or more and maybe MIDI input or some other way to change the notes, you could do a very, very simple kind of tone wheel organ simulation here, where each knob is sort of setting the overtone as it would in like a Hammond organ. Wouldn't sound quite like a Hammond organ for a lot of reasons, because this is perfect sine waves. First and foremost, that's the main reason, but it would sound organ-ish, and that could be an interesting instrument you can make with this technique. Any questions
Really cool.
so far about this?
Yeah, I don't see anything from the chat. Guys, feel free to ask anything, or if you're curious about certain things that are a bit more advanced than this or more theoretical, feel free to bring up any suggestions. To me, I think that what I would love to know is it's maybe, I guess, more on the coding side of this. Like if you would want to add now 8 and you just have 4 knobs, is there a quick way of, I think I lost you. Did I lose you? Can you guys see Nick? I don't. Uh-oh.
Hello?
Nick, you're back.
I'm back. Okay.
Yes. Um, yeah, okay. Nick is
Am I
gone. Nick is
back on the
gone.
stream?
Okay. Uh, there is a bit of a delay, but we got Nick back. So hopefully you can see him now, and I can see that you also
Okay.
have. Oh, I see that you also have a few questions.
Yeah, apologies for that. Home
Void synthesis.
network in the suburbs, and my wife works from home, so if she's on a video call too, this may happen. We'll see what happens.
Yes. Okay, so I'll hold back for my questions. I see here a question from Michael.
Yeah.
What is the maximum number of signs possible with Daisy ignoring overhead for reading knobs?
Ignoring the overhead for reading knobs. So, I mean, that is a question that I don't think is possible to answer easily. The next example we'll look at, I'm using 128, and it runs fine and is not a very optimized patch. So, as we'll see with the way the harmonic oscillator is implemented using a pretty efficient technique, using a mathematical phenomenon or mathematical theorem called Chebyshev polynomials, which are pretty cool. It's a pretty efficient way to do additive harmonic synthesis. I'm able to do 128 in Daisy Duino in a pretty unoptimized patch. I think if you optimized it, you could do significantly more than that. Whether that is going to be useful or not also depends on a few factors. You can only kind of extend your harmonics up to the Nyquist limit, which is 1/2 of your sample rate. Beyond that, you're just going to alias. So there's really sometimes there's not much point in doing too many harmonics. In fact, you have to account for that if you're playing a higher note and the harmonics will extend beyond that limit. You want to just silence them. The harmonic oscillator does that for you, so you don't have to worry about it. Yeah, short answer, it really depends on how optimized your patch is, but I've been able to do at least 128. I'm sure it could do more.
Neil is asking if where is it? Yeah, you don't really have any input for the pitch. So how
Right.
would you control that?
Yeah, the next patch that we're going to go through also has one of the knobs mapped to pitch, but if you had an analog input for pitch, just you would do an analog read and then scale that to the frequency you want. So just like the other oscillator object in Daisy SP, and I think many of them have the same convention of set freak, and then you set that in hertz. You need to, of course, scale your knob appropriately for pitch. You'd want to use what Daisy calls mapping log to its equal octave spacing. So you'd want to make sure that you're not using a linear mapping if you're using frequency, but we'll see that in the next patch. One of the knobs is doing that for the pitch. You could do that with CV as well, because that's also just an analog reading, but that would depend on the convention you're using. 1 volt per octave would require specific scaling. And if you were doing MIDI, you just interpret the input. I don't have an example here handy for that. There are some, I think, in the examples library for Daisy. On a note on event, you would just interpret the note number, map that to the appropriate frequency, and then set freak on the harmonic oscillator, just like many of the other oscillators.
Yeah, so the harmonics that you control, each of their amplitude will always follow the set freak function.
That's each of their frequencies will always be a multiple of whatever you put here. Also subject to set first harmonic index. So if this were 2, then my first harmonic would actually be the second one. So if I set freak to 220, it would actually be 440, and then so on and so forth, integer multiples. I don't have I mean, I'm sure there are creative uses for that. I don't have one offhand. Like I usually just leave this at 1 so that my first harmonic is always the fundamental, is always equal to this number.
Sophie's asking, would it be possible in this setup to add a control for spread? As in collapsing all harmonics? Yeah, you know what it means.
I'm not sure I do know what spread means in this context.
Spreading the frequencies. So, as in collapsing all harmonics into a single note, or spreading them gradually to octaves.
Okay, so so actually creating inharmonic ratios then. So if I understand correctly, you want to collapse them all into a single frequency and then have them sort of spread out incrementally from there. Would technically be inharmonic because they're not integer multiples of the fundamental frequency. They could all be a fixed spacing, but unless they're integer multiples of the fundamental, you wouldn't call that harmonic. With the harmonic oscillator, no, you can't do that because of how the harmonics are derived in the DSP. They have to actually be harmonics. That's how Chebyshev polynomials work, as we'll see shortly. But with another technique, if you were just summing, sine oscillators or doing a bunch of table lookups, you could do whatever frequencies you want for each of them and then achieve that sort of spread control. Not with a harmonic oscillator, though. It's a good question.
Nice. If we do try to do this with just sine waves, like raw sine waves without that approach, then how many oscillators can we actually safely use?
Not too many. I mean, especially with the default oscillator in DZSP, it's using just a standard standard library sine sine function, which is not efficient. So it's really not an efficient way to do a sine wave oscillator. I mean, it's fine if you just have one, but if you were doing multiple, you'd want to use like a table lookup or some other technique for generating individual sine wave oscillators and adding them. As we look at the code for the harmonic oscillator, if you were doing an optimized lookup table with, wrapped angle phases to get the harmonics, this is probably a little advanced to speak about without qualifying it, but it's a whole other tangent to actually talk about what all that means. If you were doing that, it's actually fairly comparable. It's just a few arithmetic operations per harmonic. But with the typical DZSP oscillator object, you would be able to achieve significantly less because it's not particularly optimized. It's actually pretty slow.
You know what I'm thinking now, and maybe guys, you can comment if you like that idea. Maybe we could create a weekly challenge after these workshops where people could play around with the knowledge that they received in the workshop and come up with your own ideas and share them on Discord, and we could see if we could like make an instrument out of something here. Because for me, like, this is actually pretty exciting. It sounds like something that could be created into something very unconventional. Maybe like the feedback synthesizer that Nick created, the Audrey 2, that is not really something that you would expect a synthesizer to behave this way. It's quite of a niche and a specific thing. But it comes from like exploration of ideas, and this seems to me like something that could be explored into all sorts of ideas of like user experience with additive synthesis and harmonic oscillators.
Definitely. Yeah, that sounds really cool. I would love to see what people are able to come up with some of this knowledge.
Yeah, so if you guys like this idea, comment, and I'll see if we can try to organize something a bit more organized, maybe with prizes and stuff. I guess we could probably do something like this. Give you simple boards and stuff. Okay, let's continue. Nick, what do you have for us next?
Cool. So let's talk a little bit about how the harmonic oscillator works, and then let's go into more general additive synthesis topics, which will, I think, lead nicely into the second example that I prepared. So I've mentioned a few times so far, but not really gone in depth. The harmonic oscillator, this is, by the way, ported from Mutable Instruments code. So I'm not sure exactly which instrument uses this oscillator, but this is code that Emily wrote originally that has been ported into DaisySP. The harmonic oscillator itself, here's the class from DaisySP. Like I mentioned, it's a template class. So if you don't use that syntax that I used here to specifically provide it with a number of harmonics, the default will be 16. But that's, how you would tell it. If you want 128, then you put 128 here in these brackets, or change this to 128. Yeah, before we go, I don't know that it's going to be the best use of time to really dive deep into the code here. Anyone can actually go and read this. But if we look at the header, we'll notice it says it's based on Chebyshev polynomials. And Chebyshev polynomials are a mathematical mathematical definition. I'm not really sure what the right word is here. I like this page from Brilliant. I found this, which I can also make note of for when we share materials for these classes, which I think we also need to figure out what the best place to do that is. This kind of walks through the definition, but essentially Chebyshev polynomials, to put it simply, are a very efficient way of recursively deriving multiple angles of a sinusoid from one sinusoid. So if you have, say, a cosine wave or a sine wave, you can get twice the frequency, 3 times the frequency, 4 times the frequency through this mathematical definition in a pretty simple recursive way. And when I say recursive, I mean each octave. So the sample that we're calculating on the DSP side, if we apply this to DSP as the harmonic oscillator does, the sample we're calculating for each harmonic is based on the sample we got for the previous harmonic. So rather than each time doing a fresh, a separate oscillator, a separate phase lookup, we can actually get each harmonic from the previous one in a really efficient way. We don't have to go too far through the math here, but here, if we look at these two figures here, so these are based on trigonometric identities, which they do explain on this page. So the cos of 0, so cosine of 0 times anything is 0. Cos of 0 is 1. Cos of 1 theta, theta is our angle here, so this would be like our frequency, is just cos of theta. Cos of 2 theta can be defined this way, 2 cos squared of theta minus 1, so on and so forth. These go, you can find the full definitions on Wikipedia all the way up to, like, I don't know, whatever number they stop at. But if you sort of redefine this as t sub 0, where 0 would be our harmonic, where the zeroth harmonic is just DC, so it's just 1. The first harmonic being the fundamental. If we redefine the cos theta term as x, then we see this as these are simple polynomial equations. This is just x, t2, so the second harmonic would be 2x squared minus 1. If we substitute cos theta for x, then we get what we see up here. So these are sort of like, for each harmonic, this is the actual drawn out formula. But there's a really simple recursive relation we can find here that they derive through here. And I'm not going to walk through all this since this isn't really meant to be like a math heavy lecture. But we can see t sub n plus 1, so that's the next harmonic, is equal to 2x tn of x. So that's our current harmonic minus the previous harmonic. So this is a recursive relation. For every new harmonic, we're defining it in terms of where we are currently and where we've been before. So this is directly reflected here in the code, where it's in the process method, which is here. So there's some stuff here to deal with the harmonic indexes and stuff like that, and a single phaser. So the phase, this is just whatever we set the frequency of the oscillator to. We're incrementing that phase based on our sample rate and the frequency of the oscillator. This is the really standard thing for most oscillators in DSP, if not all. And then if that goes over 1, we subtract 1, so that we're just wrapping this between 0 and 1. And then here you can see for all the harmonics, we're looping through, and we've got our current sample. So this is the whatever we started with, usually the first harmonic, the fundamental, which was a sine lookup. We can see up here. That we need to calculate is 2x times the current minus the previous. And that's exactly the same as we see here. 2x times the current, which is t sub n of x, minus the previous, which is t
And
sub
Nick,
n minus
you dropped off for just a split of a second. Maybe you could just
Okay.
repeat the last sentence.
Yeah, I was just sort of drawing the direct parallel between this code and the recursive definition of Chebyshev polynomials that we see here. 2x t sub n of x minus t sub n minus 1 of x. That's exactly what we see here. 2x, which is a variable that we calculated above, times the current minus the previous. So here in the code, which again, I don't know, unless there are specific questions, I don't necessarily want to walk through this in detail as if it were a lecture, but you can see the direct parallel between the mathematical definition here and what we see in the code. So for each harmonic, so to sum them together, this is our output sample. We're taking the amplitudes that we set on the oscillator times the current sample for the current harmonic. So that's what's doing that scaling for each harmonic. And then we're just doing a little bit of math to calculate the next one. It's here we've got a temporary variable assignment. We've got one multiplication and one subtraction. So for each harmonic beyond the first one, that's all we have to do. Just a few simple arithmetic operations, and we've calculated the samples for our new harmonics. This is comparable, if not better than, in some cases, doing table lookups based on multiples of the wrapped phase. So this is a really efficient way to do this. I will pause there because I also have a graph here that we can kind of look at how this works in this great graphing calculator tool, Desmos. But I'll pause there to see if there are any questions before we go into that. And the whole gist of this is just that this is a cool mathematical technique that allows very efficiently generating pure sine wave harmonics from a fundamental.
It seems that it's clear. Let's continue.
Great. So yeah, I've got just a graph here in Desmos set up that sort of demonstrates some of these concepts. So from here, we've seen that our first harmonic, just our 0th harmonic, is 1. That's just, we need that for the math, but that doesn't really map to anything in what you hear. The first harmonic being t sub 1 is x, or cos theta. We've got that here as well. So our first term, I've got them as s here, is just 1. And then our 2x term is 2 sine x. And that's exactly what we're seeing in the DSP code. So this is just some initial definitions to sort of set this up. And we see for each of these, this is a recursive definition. Tx, which is 2x times the current minus the previous. So we start with the S1 minus S0, S2 minus S1. So these are all recursive. You see the previous function is used in the next function. And if we look at the highlighted waves, when we do this, you can see that each of these is a multiple of the previous frequency. It's a little easier to see if you use cos here instead of sine. It doesn't really matter. The math mostly works out the same. The only difference is phase. So we can see that we're increasing up to 4 harmonics here for each of these. And this is just with really simple recursive math. And then we've got sliders up here for the red graph, which is the sum of these harmonics scaled. So this is exactly the same thing that we were hearing on the simple fix. So you can imagine these sliders as being the knobs. For each of these, we're increasing the amplitude of the harmonics. And we can see the results graphed as we do that. So if we bring all these down to 0, let's say, and just turn up the 4th harmonic. So this is 4 times our fundamental. And if we add that to the fundamental, we get this funky shifted thing. So yeah, this is working exactly the same. The math that you're seeing here, graphed here, and the math that's in the harmonic oscillator code translates exactly to what we're hearing and we're seeing in the result. So Chebyshev polynomials are pretty cool, efficient recursive way to generate a lot of harmonics. I mentioned the only difference between cos and sine here is the phase. You see cos, these are all the same phase. They all start at 1, all of these other harmonics. They all start at 1 right there and then begin their oscillation. If we use sine, just the way the trigonometric identities work out, we end up with a phase shift each time. So otherwise, the sound is essentially the same, and phase in this situation only really matters for the shape of the wave, not necessarily the sound, unless we're changing these really rapidly. The phase relationship between harmonics in a waveform does matter in some cases, but for these simple examples does not really matter. We'll see a case where it does matter shortly as we look at how to extend this to sawtooth and square waves. Cool. Looked
Really
like we
cool.
had some chatter.
Yeah, some people are referring to the fact that it was dead for a moment.
Okay.
But we do have a little bit of a gap, so we did have a question before that. So Neil was asking, are the harmonics always an octave apart? Yeah.
Good question. No. So the harmonics will be an octave apart if the n of the harmonic is a power of 2. So the harmonics are, let's look at VCV because we can see this really clearly. So here, this peak is approximately 220 hertz. So that's our first harmonic, our fundamental. The second harmonic, this will be 440. So about 440. That's an octave apart because that's 2 times the fundamental. The third one, however, will be 3 times our fundamental. So if our fundamental is 220, the third one should be 660. So this is 660. So that's not an octave. That's an octave plus a perfect fifth. But then the fourth one, 4 is a power of 2. This is an octave. So 880. So for each power of 2 times the fundamental, we have an octave. And if you do that recursively, so each octave, each frequency, when you multiply by 2 again, that's the same thing. That's just geometric series of powers of 2, 220, 440, 880, 1720, etc., or 1760, sorry. So harmonics are not octaves. Harmonics are integer multiples of the fundamental frequency. Octaves are powers of 2 harmonics. So 2 times the fundamental, times 2 again, times 2 again. We're skipping a bunch in between. That's how you go up octaves. That's a great question.
If we want to shift one of them to make something a bit more odd, that's not really possible with this technique.
Not possible with this technique, correct. You would need, because this is designed, the way this math works out is for integer multiples of our angle, our frequency. So that allows exact harmonics. If you wanted something slightly inharmonic, you would have to use a different technique, separate phasors or separate oscillators, summed together.
What would happen if you would just add a pitch shifter after this? I mean, could you control? No, you can't really put a pitch shifter on only one harmonic. You would actually put it on all of them.
Yeah, if you put it after the output, you would. If you put it after one harmonic, I mean, there are many different techniques for pitch shifting, but pretty much all of them incur some amount of latency. So you could do that, but as you shift things around, that one harmonic would be delayed relative to the rest of them. So that would be, maybe not the purest way to do it. Experimentally, yeah, you could do something like that if you change this code and stuck a pitch shifter in here for one of the harmonics. Yeah, the results would be kind of probably a little strange, but Yeah, there's no
But
reason you
never
couldn't do that.
know.
Yeah.
Okay, John is asking, what is the relation between pitch and the amplitude of the different harmonics you demonstrated using the sliders?
Pitch and the amplitude of the different harmonics. Well, you still kind of hear that. So here's just the fundamental, just 220 hertz, A3. You hear that as A3. If we turn these up, you still kind of hear that note as A3. You hear it relative to the fundamental. That's kind of the pitch you perceive. If we take away some of the harmonics, you might perceive that differently. You might perceive it an octave up. But generally speaking, the perceived pitch of a sound is sort of the least common multiple, or the least common denominator of all the harmonic ratios in the sound, if we're talking about like pure harmonics. So yeah, I'm not really sure how best to answer that question. I guess like the harmonics of a wave determine, the overtones or sort of the spectrum of the sound that we're hearing. If they're purely harmonic, the perceived pitch will be the fundamental, unless there's like a bunch missing and maybe you've got the second harmonic and the fifth harmonic and the eighth harmonic, then you might not hear that as whatever the fundamental you calculated those harmonics from is. But as long as the fundamental and or most of the harmonics are present, you will hear the pitch as whatever the fundamental is. That's how you perceive that pitch. So the amplitudes of the harmonics doesn't necessarily play that much of a role in it unless a bunch of them are missing completely, including the fundamental.
And maybe there is something to say about like marimbas and like in general all sorts of things you would bang on, like bells that might get like that you have the fundamental, but it isn't necessarily the frequency that you're actually hearing, like that. Yeah.
Right. Yeah, because oftentimes either higher harmonics or in the case of many percussive instruments, they're actually inharmonic. It depends on the instrument, of course, but many of them create inharmonic partials. So they're not actually multiples of any particular fundamental. There's some other strange ratio based on the physical properties of the material. So yeah, you're absolutely right. Like a marimba and other xylophone or mallet type keyboard instruments, oftentimes the fundamental is not the strongest harmonic. So you might hear it as the third harmonic or whatever is really strong. You might not hear that as whatever the fundamental is. You might perceive it, especially in isolation with no other sounds happening, you might perceive it as a different pitch. But for other percussive instruments, the fundamental is somewhat indefinite. The actual partials that you're hearing that sort of resonate in whatever physical body is vibrating are inharmonic in some cases. And in that case, like the pitch you perceive it as is a little more complex. If you perceive it as any pitch, it may just not sound pitched at all.
Yeah.
Like a cymbal. What's the pitch of a, hitting a crash cymbal?
Yeah. But now I'm thinking actually about that idea of like hacking some inharmonics into this. What if you would actually take the harmonic information, you would add additional oscillators on top of it that would follow some of the harmonics of the harmonic oscillator, but then added, and like you would be able to control with a knob or with like a touch sensor the amount of it feeding into the sound to create new kind of timbres.
For sure. Yeah. You could sort of shape, really, when you're talking about additive synthesis at all, which this is, we're adding harmonics rather than starting with a lot of harmonics and taking them away. You can kind of shape it however you want. You don't even have to use pure harmonics. I think like you're suggesting, you could add another oscillator that tracks the fundamental by some inharmonic ratio, just to add another peak there in the spectrum. Which if you were using a different technique for pure sinusoidal additive synthesis that's not the Chebyshev harmonic oscillator, you could do that. You could have arbitrary frequencies, amplitudes, and phases of your sinusoids. With this technique, you can have arbitrary amplitudes, but you can't have arbitrary frequencies, only harmonic ratio frequencies. And also you cannot have arbitrary phases, which is an interesting limitation of this technique. And we'll see why that's important when we start looking at how to extend this into like, more familiar wave shapes by scaling the harmonics appropriately.
Interesting question from Nick, from Neil. I wonder what adding a tiny but random noise into the Chevy calculations, would that just sound terrible, or does this make any sense?
It would probably sound like noise. I don't know. I would have to think about that and think about how the math would work out. But if you added a little bit of noise at each harmonic step, it would probably start to sound like noise pretty quickly. Could be interesting though, if it were periodic noise or some periodic variation. You just have to do the math and see how that would work out. Hope you like trigonometry.
Yeah, I think it has so much potential. Like, I wonder how many harmonic oscillators can you actually use at the same time?
Yeah, that's a great question too. It just depends on how optimized your code is and how many harmonics are in each one. I'm sure you could do a reasonable amount of polyphony with a well-optimized patch. These ones that I'm doing today are purposely not particularly optimized, and there are some downsides to that. But yeah, you could certainly have like a polyphonic patch with multiple harmonic oscillators.
Nick is asking, when you were talking number of signs, were you referring to instances of harm oscillator or 128 harmonics with one fundamental? I got lost.
Yeah, the second one, 128 harmonics, including the fundamental. So the fundamental is included in that 128.
Cool.
Yep. Cool.
Let's continue.
Great. Cool. So if you've ever studied signal theory, specifically musical signal theory, you may have seen this before. These are this is a summation of sine waves where for each n in our sum, so n varies from 1 to capital N, and capital N is controlled by this slider. N is a multiple of x, so this is sort of like multiplying the angle, which is equivalent to multiplying the frequency by another integer every time for every step of n, and then the amplitude of that summation term is divided by n. This is how we decompose a sawtooth wave into its constituent harmonics. This is like Fourier analysis. Imagine a saw wave that is infinite. It just goes on forever. A perfect saw wave that never changes frequency, just always a saw wave forever. The Fourier decomposition, which is a mathematical technique for converting time domain into frequency domain, analyzing sort of the sine components that go into a signal. This is what that looks like. So as I increase n here, what this slider is doing, this is like our number of harmonics. We start with 1, we just got a sine wave. As we start to add them, we see that this starts to look more and more like a sawtooth. So this is something that we can do with a harmonic oscillator. We just need to scale the amplitudes according to this, which is actually really simple for a sawtooth wave. The amplitude of each harmonic is equal to 1 over the harmonic index. So n, our fundamental, would be given an amplitude of 1. The second harmonic would be given an amplitude of 1/2. The third harmonic, 1/3, so on and so forth, just increasing that denominator each time. Technically, phase is important here as well, but in this case, we're just kind of looking at it the way you would look at it, as if the rising edge centers on 0. And we get a sine wave, a sawtooth wave from this summation. We can also do the same with the square wave, which is only the odd harmonics. So for each n, we take 2n minus 1, which gives us an odd number every time. So this looks pretty much the same. We're just, instead of n, we're using 2n minus 1 as the term here for the frequency scale and the amplitude denominator. 2n minus 1 gives us an odd number every time if we start with n is 1. So if n is 1, then we have 2 minus 1, which is 1. If n is 2, we have 4 minus 1, which is 3. So we're only getting odd harmonics. And from that, we can see that as we increase the number of harmonics, we have a square wave. So this is a way to additively synthesize familiar subtractive wave shapes. Pretty much every subtractive synth in the world has a sawtooth and a square oscillator shape. And this is how you would do the equivalent with additive synthesis by summing all the harmonics.
Small question about this.
Yeah.
You know all these variable oscillators. Is this the technique they use to do that?
No. Almost never, unless it's specifically an additive oscillator. If you're doing the DSP for variable shape oscillators, I mean, if you're doing the DSP for any oscillator, really, you can kind of think of the perfect case. So for every sample, we're sort of drawing like a perfect descending ramp. But the problem is that you get aliasing if you do that. So really, most of the time, if you're talking about geometric shape oscillators in DSP, unless they're specifically meant to do circuit simulation or be analog modeled, if you're just going for like perfect geometric wave shapes that are not going to alias, you kind of start with just the simple perfect geometric shape, and then you handle the discontinuities. So these areas where we're jumping from 0 to 1, that's where all the higher harmonics start to matter in defining the shape. So you just need to handle that. And most band-limited synthesis techniques, including a lot of variable shape oscillators, that's what they're doing. They're just sort of like perfectly simulating the geometric shape and then handling the discontinuities to mitigate the aliasing. That could be a whole other discussion, but generally that's how that would work.
Yeah, I think there is an example. There is an oscillator like this on the DayZ library.
Yep.
Might be
BL-OSC.
for another.
Yeah. And well, there's BL-OSC, which I think can do I can't remember, but there's also variable shape oscillator, which I think is ported from mutable code. So anyway, yeah, that could be another topic. But yeah, unless it's specifically advertised as an additive synthesis engine or additive oscillator, then typically they'd be using different techniques for that.
Nice, thanks.
Mm-hmm. Looks like we might have. Do we have another question? Oh, nope, not yet. Okay. Yeah, so let's take a look at what this looks like in practice. So I'm going to open my other patch. And I have to bear with me a moment while this compiles, because Arduino compilation can take a while sometimes. So I'm going to flash this onto my seed. But we'll see right away, this is a little more complicated. It's almost 3 times as much code with a lot of math here in this one function called calculate amplitudes. But this patch does some pretty cool stuff that you tend to see in more full-featured additive synth engines. All things we can do with the harmonic oscillator. Really, if you think about the harmonic oscillator as like a canvas on which to create interesting synthesis patches, scaling and modulating the harmonics in different ways is kind of what you're working with. That's sort of the box that you're working in. You could use envelopes to scale the different harmonics. You could use LFOs. You could use sort of like shapes to apply to, if you think about all the harmonics in an array, what if we sort of mask that array with a shape? What if we like start to roll off the amplitudes of the higher harmonics? That's a really good example, because what you're going to get there is a low pass filter. We're just attenuating the higher harmonics relative to the lower ones. That's essentially the same thing as a low pass filter in a purely additive way. The sound will be a little different because low pass filters, especially the ones we really like the Moog filters and the analog modeled filters, are actually a lot more complex than that and create some of that warmth in the sound that we like through nonlinearities. But this as a pure way of doing a low pass filter actually does work, and we'll see that in this patch whenever it finishes compiling. Okay, here we go. So now it's flashing. Great. Okay, cool. So let me pull up VCV so we can see. So right away, we can kind of see that we have a lot more harmonics here. This one has 128 harmonics. And if I can get the scope to work here. There we go. So what we're hearing now, believe it or not.
Lower the volume slightly bit.
Oh, yep.
Maybe a bit.
I know it was a little quiet last time, so I was trying to overcorrect. So this one actually I can change the pitch. Let me just turn up the gain. That'll help. There we go. This one actually can change the pitch. What we're hearing right now, believe it or not, is actually a sawtooth. It doesn't look like a sawtooth. Why doesn't it look like a sawtooth? Phases. So this is the exact formula right now we're hearing unfiltered for generating. Oh, there it is. Sorry, I had it on the. There we go. This is actually a sawtooth. So for each increasing harmonic, the amplitude, and this is a decibel scale on the vertical axis, so it doesn't look like 1/2, let's say, linear. Can we zoom in on this axis? I don't think so. Unless I give this a whole bunch of gain in between. Let's try that so we can... well, anyway, I'm not going to bother with that right now. Each harmonic is scaled by 1/n, where n is the number of the harmonic. So if you look at the scope, obviously that does not look anything like a sawtooth. It looks like this weird curve shape. That's because we're limited in what phases we get out of the harmonics in the harmonic oscillator when we're using the Chebyshev technique. So to demonstrate that, if we look here, so here we've got sum of sinusoids that looks like a sawtooth. If we use cos instead, that looks like this. That's inverse of what we're seeing on the scope there, but it's the same shape, this weird curvy, peaky shape. By changing sine to cos, all we've done is changed the phase of the individual sinusoids that go into the summation. Cosine is a sine wave shifted by 90 degrees. So we can do the same thing if we do minus n pi over 2. Whoops. N pi 2. Oh, or sorry, n minus 1 pi over 2. Here we go. So if we wanted to get that to look like what we're seeing here, we do n plus 1 pi over 2. So each of these sinusoids, as we're going up the harmonic summation here, is shifted back by pi over 2 times the harmonic index. That's what happens when you do the Chebyshev summation with a sine, just due to the way the trigonometry works out. So here we see, like, I didn't change any of the amplitudes of these harmonics. All I changed was the phase. All I did was subtract a constant term from the sine wave, which is a phase shift of the sine wave. And we get this weird shape that sounds exactly like a sawtooth, but doesn't look like a sawtooth. It sounds like a sawtooth if we're listening to it by itself. So that matches exactly what we're seeing here. So that's when I said earlier that phase was important, that's what I was talking about. And if you're noticing this little orphan peak down here, this little dude right here, that is just noise because I'm powering the simple fix over USB and it's creating a slight ground loop. So that's just noise from the USB. You can see that that's the case because it stays in the same place. If I change the pitch, that little peak stays in the same place. So it's not relative to the pitch. It's just some noise on the line. So yeah, that's one really interesting artifact of this technique, the Chebyshev polynomial technique for generating harmonics efficiently, is that we don't have control over the phase. The phase is just each harmonic's phase is fixed at what it is, and what it is ends up looking like this. So even though we're hearing what sounds like a sawtooth wave and looks like a sawtooth wave in the spectral domain, in the time domain it does not look like a sawtooth wave. It looks like this weird curve shape. that's interesting, right? I think at one point, I haven't tried this yet, but at one point, somebody in the Synthux Discord were talking about phases in this on this topic, and for a square wave, which so there's a square wave. That doesn't look like a square wave. That looks like some weird like lattice thing. If you put a square wave through a wave shaper, it doesn't really do anything because you have nothing to really fold back. It's just a square peak. If you put this through a wave shaper, that would do something interesting. The wave shape actually matters if you put this through a wave shape. So you could actually have a square wave do something in a wave shaper if the phases are as they are here. So I'm going to pause there because I want to make sure that makes sense. The summation of all these harmonics, according to this formula, to get the proper scaling to get a sawtooth wave or a square wave, we can do that with our Chebyshev oscillator. That's what the seed example that I'm running right now is doing. But the phases will not be the same as what we see in our perfect summation here. They'll actually be shifted. So we get a very strange looking wave shape. But spectrally, as we listen to it and we look at the spectrum, it's exactly the same thing as a sawtooth.
I'll wait for people to ask questions. In the meantime, I wonder, you threw the terms folding and wave shaping. Is this what it is really? Adding sine waves to this to one fundamental is wave folding or wave shaping?
No, wave folding and wave shaping wave folding is something specific. Wave shaping is sort of a more broad term that refers to like anything that sort of reshapes the sort of waveform itself, which has spectral and timbral connotations, of course. So wave folding could be considered, I guess, a form of wave shaping. But wave shaping could be like saturation, right? If you take a sine wave and you drive it too hard and it starts to soft clip, you're sort of squashing the peaks of the sine wave. We're not doing anything additively there. Like that's not a spectral domain technique at all, but it changes the shape of the sine wave. It now squashes sort of the top and bottom where the sine wave comes around, and it changes the sound of it. It does actually result in a harmonic change in the sound because the waveform is still perfectly periodic. But wave shaping and wave folding generally are more like time domain techniques, or like we're actually messing with the amplitude of the final waveform rather than like additive synthesis could be considered kind of a spectral technique because we're sort of building up a spectral signature and a timbre based on the harmonics, which constitute the spectrum of the wave.
Very interesting.
But when I said wave shaping, I meant like, if you wave shape, that was kind of a little bit of a tangent. But if you put a square wave through a wave folder, it doesn't really do anything because what it's doing is folding back the part of the amplitude that exceeds a certain threshold. And with a square wave, it's kind of just like perfect flat, flat top and flat bottom. If you fold that back on itself, you're just lowering the amplitude of those flat areas. But with this, if you fold this back on itself, you can kind of imagine that peak sort of inverting. I might be able to, if I have a wave folder, I'm not sure I do. Wave folder. Yeah, here we go. Dual channel wave folder. So if I put that through a wave folder, we're not going to be able to hear this because I'm just using this to visualize the signal, but we can apply this to the signal. So if we do this, then I got to turn it back up. I'm not actually sure how this wave folder works, but in theory, we should be able to chop off the peak. Yeah, that's what I get for trying to do it live. Oh, maybe it's this. Trying to do it live. I don't know. I don't know how this wave folder works, so that was a failed attempt to do a live demo that didn't work at all. But in theory, if you put this through a wave folder, these peaks would sort of like invert on themselves and you get a really weird wave shape, weirder than the one we're seeing. But I find it super weird that what we're hearing is a square wave and what we're seeing is this weird lattice. That just all has to do with phases of the harmonics.
And it also sounds like when you're cutting with a cutoff, it sounds like it's like a resonant.
Yes, exactly. That's what I designed it to be. So we can take a look at the code, but this knob is acting as a cutoff. And I specifically designed the math. It's a little flawed and probably not great math, but I attempted to design the math to sort of spectrally shape it like a resonant filter. So here, if we turn this up, we're actually turning the resonance up.
That is so awesome.
And that's not a filter, that's just by shaping the harmonics. This control, by the way, on the final one, so this is pitch, and this final one is the even odd bias. So in the middle, we're hearing all the harmonics. If we turn this way, that's only the odd harmonics, and that's why it sounds like a square wave now. And we can see that in the spectrum. Every other harmonic starts to become attenuated. If we go the other way, now it's only even harmonics. And when we do
interesting.
Yeah, when we do even harmonics, the effect that actually has in the absence of the fundamental is an octave shift up, because we're still, if this is our new fundamental, so one octave from our original fundamental, so say this should be like, I don't know, if let's assume it was 440, then the even harmonics from the original signal, actually correspond to integer multiples of our new fundamental here. So this is an octave shift up. It's still like a sawtooth in its spectrum. It's just an octave up because we've limited it to only the even harmonics of the original signal. So that's kind of like, that's variable shape, to answer your earlier question. That's like variable between saw and square, and all we're doing is just attenuating every other harmonic. And that works if you've got the filter on too.
That's really cool. Hey, this I don't know if it makes sense to bring this up now, but Warp Core, your module, and this VRAC module, I remember you mentioning like there's no filter there. It's all additive, but I'm assuming this is a bit of a different technique than that.
Yeah, it's very different. Instead of adding harmonics individually like we're doing here, that is using phase distortion, which is a kind of a weird wave shaping technique that pretty much exclusively a digital thing. But I'd be happy to talk about phase distortion maybe in a future video.
Cool.
Because it's pretty cool too. Obviously, if I'm making a module out of it, I think it's pretty cool.
Yeah.
Cool.
Yeah, let's continue.
Yeah. So basically this patch, you'll see number of harmonics is actually 128. So there you go. That's 128 harmonics in the harmonic oscillator. What I mentioned before, and this is really important for how this harmonic oscillator works as well, it actually stops producing harmonics once it reaches the Nyquist limit. So that point at which it would start to alias, it stops producing harmonics. So I don't know if I can visualize this without applying a lot of gain. Let's do that. There we go. Okay. So you can see right here, sort of like that's 128 harmonics from a lower pitch. It stops around like 16K or so, because that's just where that harmonic happens to land, the 128th harmonic. As we go up, you can see it's getting closer and closer to the Nyquist limit, which is in this case 24 kilohertz, 1/2 our sample rate. So the harmonic oscillator actually applies kind of a tilt internally. It starts to ramp the harmonics down as they approach Nyquist. I think just for like timbral niceness, there's really like no technical reason in sampling theory that it has to do that. What it has to do is make sure that all the harmonics that would go above 24 kilohertz are 0. And you can start to see that as we go up, that it completely cuts off all the ones that would go above 24 kilohertz. And again, what you're seeing a bunch of crap on there on the scope, unfortunately, due to the USB noise. That's like, yeah, I'm putting 0 out of the codec right now. So that's just the USB noise. It's kind of making it hard to see that this is not actually aliasing, but it's not. That final harmonic there, right here, that's the last harmonic that has any amplitude. After that, it just zeroes them all out so that they don't alias. So it's doing that internally. It's just kind of a nice thing that the harmonic oscillator implementation from Mutable does. But yeah, that's why we can have 128 harmonics, and even at higher fundamentals, we don't have to worry about aliasing. It just handles silencing the ones that would alias. The actual audio callback here looks pretty much the same. We've got like a scale factor, which is something you have to handle here. The more harmonics you add, the higher the output amplitude can be as the harmonics start to overlap, as the samples start to overlap. The maximum output amplitude can get higher. So you kind of want to scale the amplitude based on how many harmonics you're producing to kind of normalize it. Is one way to do it, or you can just like be really conservative and multiply it by some low number and make sure it's quiet all the time and would never clip. But that's something you do have to handle. Otherwise, the audio callback is really simple. All we're doing is processing a sample out of the harmonic oscillator and multiplying it by a volume scale. Our setup looks really similar. Instead of clearing the amplitudes like we did last time, we had 4 amplitudes and we were clearing them. Here we're just calling this calculate amplitudes function, which we'll look at in a second, and that's what's actually like setting all of the values of all 128 harmonics each time. And then here in the loop, we've got frequency, which is taking one of the knobs and mapping it to MIDI note numbers and then converting that to a frequency. We've got cutoff, which is doing a they call it log. It's not really logarithmic, but it's the log scale mapping in DAISY-SP's fmap to give us a particular flavor of exponential mapping between, in this case, something very close to 0 and 1. So our cutoff is here not specified in hertz. It's specified in the 0 to 1 being sort of the entire spectrum that we have to work with. So 0 hertz to 1/2 the sample rate. The cutoff is what percentage of that, where that cutoff is. And that just made the math work out a little easier when using this technique than using actual frequencies. You could do it with frequencies with slightly different math, but that's why that's set up that way. The resonance is just 0 to 1, so that's just a normalized read. And then this even odd split is a value from -1 to 1. So in the center of the knob, it would be 0. And that's when we're not biasing towards even or odd harmonics. We're just biasing them all equally. Then I've got some one pole smoothing here, really pretty heavy smoothing on the cutoff and resonance knobs. The reason I have that is because the ADC reads from Arduino are only 10-bit and they're pretty noisy. They're less noisy using the technique that libdaisy does, but here they're kind of noisy. And if you've got the cutoff and resonance values kind of having noise in them, changing like every time we calculate them without any smoothing, then you hear that in the result. You like see it jumping around a little bit. So this is just like heavily smoothing the readings to kind of like help avoid some of that noise. The scale is, so calculate amplitudes, updates all the amplitudes in the array and gives us a scaling factor, which we're using to scale the overall output volume. And then we're setting the frequency to whatever frequency you got from the knob and setting the amplitudes to the updated amplitudes after we've called this method. And then I've got this delay in here just to make sure the loop runs at somewhat of a fixed frequency. It's not perfect when you do it this way, but it'll be something close to 6 kilohertz so that this smoothing is actually somewhat predictable. Yeah, so to simplify, I mean, the setup is just as we usually have, just setting everything up. The audio callback is just getting samples out of the harmonic oscillator. All the magic is happening in the loop. And really what we're doing is just reading 4 knobs and calling some functions to take the readings from those 4 knobs and translate that into the amplitudes of the harmonics. So this calculate amplitudes function takes that normalized cutoff resonance value and the even odd split. And I'm not going to go through all this math, but it does a whole bunch of math to sort of turn those values into scales for each harmonic. So the scale of each harmonic is A. So A is like the amplitude of our current harmonic. And we're looping through all the harmonics and just doing a bunch of math to get, okay, based on the current parameters, what should A be? What should our amplitude for the harmonic be? The even odd one, the math is actually a lot simpler than the rest of it. So we can kind of look at this where if n, so this is our harmonic number, this is our loop index or loop variable, and this is the harmonic index. So if it's even, if n mod 2 is 0, that means it's an even harmonic. Then we want to scale it down based on how positive our even odd knob is. And remember, if it's turned clockwise, then we are emphasizing even, which really means de-emphasizing the odd ones, and vice versa. If it's turned counterclockwise, we're de-emphasizing the odd harmonics so that only the even harmonics remain. So A then is scaled by 1 minus a clamped reading of even odd. So if we're at 0, this is just 1, because 1 minus 0 would be 0. If we're slightly clockwise, let's say halfway to full clockwise, this would be 1 minus half. So then each even harmonic gets scaled down by a factor of 2 times 1/2. Same on the negative side. We're only taking negative values from here. So if the knob is positive, if this like is 0.5, this clamping means that it can't be any greater than 0. So it's just going to be 0. So this would do nothing. But if the knob is turned to minus 1/2, so we're actually in the range where we're de-emphasizing odd harmonics, this would be like minus 0.5, and 1 plus minus 0.5 would be 0.5. So we're actually scaling down the odd harmonics. So just a lot of math that we loop through for each harmonic to calculate its amplitude. And ultimately, as we saw, the result is we can get filtering, and so we can get something that behaves like a low-pass filter with resonance, and something that allows us to scale the harmonics to even or odd. So that's that's like one example of something more complex that you could do with the harmonic oscillator, just by sort of doing the math to figure out for, are we targeting even harmonics, odd harmonics? If it's in the middle, it's just the sine wave. Re-emphasizing even or odd, which ones should be attenuated, which ones should be amplified based on our filter settings via, again, just a lot of math. So yeah, it's a pretty cool way to kind of use additive synthesis to sort of simulate subjective synthesis in this case.
Great. So I think we're wrapping up, don't we?
Great. The only other thing I wanted to show, if there's time, was a more commercial version of an additive synthesis engine,
Yeah,
which I can show quickly. Make this a little bigger. So this is Arturia's Pigments, which is a very, very flexible soft synth that has a whole bunch of different synthesis methods: virtual analog, additive, wavetable, and samples. And in this case, I'm using the Harmonic engine, which is the additive engine. So if we play a note, I've got a keyboard here that you can't see, but if we play a note, we can actually see it sort of draws all the harmonics of what we're hearing, which right now is a sawtooth. It's the same kind of like every harmonic scaled down by 1/n, and we've got 128 partials, or 128 harmonics here. So some of the things you could do here are similar to what we just did on the seed. This is like a low-pass filter. It's just sort of attenuating the harmonics down to the fundamental. We can also do even-odd parity. So there's odd, that's the square wave. Here's even, sawtooth, and here's all the harmonics, and here's only the even harmonics. In this case, it's including the fundamental even when it's set to even, so it doesn't sound, it sounds like it's going an octave up, but we've still got the fundamental in the mix. But this synth can do a lot more. It can do like crazy modulations. It can do different stereo splits of the harmonics. So you get, and you won't hear that here, but you can get a stereo split, and it can do like sort of spectral shaping based on these different shape signals. So like a comb filter. So this is sort of applying this shape to the harmonics, which you can kind of see there. It's just sort of like dampening the harmonics according to like a comb filter type shape. So you can get kind of a rich spectrum based on that. You can morph between two different spectral imprints doing this. You can do tilting, which is kind of emphasizing or de-emphasizing the higher harmonics. All of this is modulatable, and you can do windowing, which this is kind of cool, and this would be maybe a fun thing for people to try on their own. So if let's turn the def down, so we've got just the sawtooth. The window, this would be like a little sort of a bump in part of the spectrum. So if we turn the size up, you can see that window there. So it's just sort of like for a certain region of the harmonics, it's amplifying them. You can make that narrower or wider. You can actually turn the gain up or down, so you can actually attenuate some of those harmonics. If you modulate the position, you kind of get like a kind of a comb filter, but just for one region. You can also do FM on the window, which I'm not totally sure what that does, to be honest. Presumably it's like modulating the window back and forth, or something like that. And it's got like, clusters. So this is not using the Chebyshev technique, because we're actually able to go in harmonic here by shifting to a cluster. Which is pretty cool.
Is this a bunch of harmonic oscillators together?
It's a single harmonic oscillator, but it's not using the Chebyshev technique, the recursive technique that we looked at earlier, because these are completely independent partials. So it's probably using some sort of optimized like sine table lookup or something like that. Or it could be using a frequency domain technique, like an inverse Fourier transform. I'm not really sure how it works. It's not open source. But it's very, very powerful. It's just sort of like adding a whole bunch of partials together based on a bunch of rules that are all modulatable. So you can do tons and tons of stuff with this, including similar things to what we saw earlier.
Is there I know the pigments is what, $200?
Something like, I don't know. It goes on sale a lot.
Is there a free additive synthesizer that we could play around with? Yeah, I guess in VCV we could probably create something.
You might be able to find one in VCV. I honestly haven't really looked. I don't know of any off the top of my head, but there may be some out there.
Cool. Michael's asking, is there a way to get a high resolution waveform over 10 bits from DAISY?
So just to clarify, when I was talking about 10 bits, I was talking about the analog to digital conversions. So the actual knob readings, reading the voltage off the knob. In DAISY Arduino, that defaults to 10 bits. That's just how Arduino sets up its defaults. I think there's a function to make that higher if you want analog read resolution or something like that. So you could make that, 12 bits, 14 bits, whatever you wanted, but then you'd have to scale it differently when you do your normalization. So if this is 10 bits, 2 to the 10th power is 1024. If it were 12 bits, we'd want to do 4096 here, because we'd get a 12-bit integer here. So I think there's a way to do it on Arduino with analog read resolution, something like that. And then you just set that to 12. I don't know if that works with DAISY Arduino. Honestly, I don't do a lot with DAISY Arduino. But in libDAISY, you can get the analog reads are better. Just to be frank, they're a lot better. They're oversampled, so they're sort of internally average, and you can get close to like 15 or 16 bits resolution, where here you're kind of doing just one read at a time, and it's pretty inefficient. So yeah, the analog reads, the control values that you're getting off of your knobs are limited to 10 bits. The actual audio pipeline is higher than that. It's 24-bit, I believe, at the codec level.
Does Surge have an additive synth engine?
Very possibly. I don't know. I've never explored all of Surge.
Yeah.
I've used some of the VCV modules, but it's possible they have a harmonic oscillator or an additive engine.
Yeah, Mike and Neil are just saying Bog Audio has an additive synth in VCV, and also there is an Additor, like ADDITATOR on VCV, that are both additive synthesizers. Okay, so Michael is actually interested in the waveform output, but I think you've covered that as well.
Yep.
Great. The reason I was asking about the open source VSTs or any like digital ones is because when designing an instrument from a perspective of user experience and playing around with ideas, when you are playing with stuff on your computer, you can come up with interesting ideas for how things are going to be working without even looking at the code at all. I know that John earlier mentioned, I don't know if I can join a challenge like this because I'm pretty new to this. It could be that you're a musician with no background in programming at all, like me. Maybe I'll put our faces here. And you come up with ideas for an instrument because you come from music. And I find it fascinating because these two approaches of engineering and design and taking your own path in whatever you feel comfortable, and then finding people to collaborate with, I think is the most rewarding kind of experience you could have in designing something, because you can never, I mean, you can be Emily from Mutable Instruments and then just do it all, but most people, most humans, it's you collaborate with people. She also collaborates with people, but yeah, I think it's something to note. I'm gonna look into how we make this into more of like a program that people could join, and we could do these challenges. And I'm even thinking maybe we could split it into engineering challenges and design and user experience kind of challenges, and then we see how we take it from there. Yeah, Nick, do you have anything to add before we finish?
No, I don't think so. Thanks for tuning in.
Yeah, thanks so much everyone for joining. If you have last questions, you can drop them on Discord and we could answer there. We're going to have another workshop on Saturday. We're going to get these to be more frequent now, which is really exciting. Bring more people who you feel like are going to be benefiting from this, and make some crazy wild stuff and share with us, because we're genuinely interested in what you guys are making and coming up with. Thanks so much, and we'll see you in the next one. Thanks, Nick.
Take care.